There's a crisis in the cosmos, and the fate of the entire universe depends on it. We've known that we live in an expanding universe since 1929, when Edwin Hubble first proved galaxies are moving farther and farther apart as time goes on. This expansion has come to underpin our entire theory of cosmic evolution, from the Big Bang to the formation of galaxies. The key factor is the rate of the expansion of the universe, a value that has become known as the Hubble constant. We thought this value was pretty set, but now astronomers aren't so sure. Do we stand on the brink of a cosmic revolution? Or could it be that our entire model of the universe is wrong? I'm Alex McColgan and you're watching Astrum. Join me as we explore the crisis gripping cosmology, revealing how Hubble's greatest discovery has become one of today's most troublesome questions. For most of human history, the universe was small, or at least we thought it was. Some ancient civilizations imagined Earth to be flat and covered by a dome of stars. The sun and moon rose and set, and the constellations turned overhead. By the 2nd century, astronomers such as Claudius Ptolemy had envisioned a geocentric universe with Earth fixed at the center, and the sun, moon, planets and stars all revolving around us. This would be the reigning model for more than 1,000 years, until the 1500s, when Nicolaus Copernicus proposed a heliocentric model, where our Earth was one of several planets circling the sun, a revolutionary idea. Fast forward to the 18th century, and William Herschel mapped some of the stars in our galaxy, the Milky Way, proving that it was a vast disc-shaped system. As antiquated as it may sound now, astronomers debated for some time whether the Milky Way was the entire universe, or if it was in fact one of several island galaxies in a much larger cosmos. That is until 1923, when Edwin Hubble resolved the question once and for all. Peering through the 100-inch Hooker telescope at the Mount Wilson Observatory in California, the world's largest telescope at the time, Hubble was able to resolve individual stars in Andromeda, and within them found his first Cepheid variable. Using Leavitt's law, named after Henrietta Leavitt, who found more than 2,400 variable stars and discovered that they could be used to measure distances across the universe, Hubble determined that Andromeda was some 900,000 light-years from Earth, an astonishing distance. Too far away to be part of the Milky Way, this proved that another galaxy with its own stars existed outside of our own. Overnight, Hubble widened our view of the universe immeasurably. But he didn't stop there. He would go on to use Leavitt's law to identify 23 other galaxies and measure their distances, some as far away as 20 million light-years from our planet. Ultimately, Hubble concluded that millions of other galaxies must exist outside of our own, forever changing astronomy. But Hubble's next revolutionary discovery also needed the work of Vesto Slipher, an astronomer born on a farm in Indiana in 1875. He joined the Lowell Observatory in Flagstaff, Arizona in 1901, and between 1912 and 1925, he made systematic observations of more than 40 spiral galaxies. At the time, it was known that the light observed from these distant galaxies could be split into spectral components, and depending on what elements were present in the light source, different patterns would appear. If the object being observed was moving away, then those same patterns would be present, only they would be shifted towards the red end of the spectrum, what we call redshift. Through years of observation, Slipher found that nearly all galaxies appeared to be moving away from us, but at the time, he didn't have a way to measure the distances to these faraway bodies, let alone their velocity. In 1927, Belgian scientist Georges Lemaitre proposed a theory that the universe was the same in all directions, and that if Einstein's theory of relativity was right, it must also be expanding. But he had no evidence to support this theory, so it was ignored for the most part. That is, until we bring Hubble back into the picture. Like most scientists at the time, Hubble was unaware of Lemaitre's theory, or of another similar one proposed a few years earlier by Soviet scientist Alexander Friedmann. Instead, from the observatory on Mount Wilson, Hubble made the same observation as Slipher, that galaxies seemed to be moving away from us. But he noticed something that nobody else had spotted before. The farther away a galaxy was, the more redshift it appeared to have, meaning the faster it was racing away from us. And this was happening in every direction. More observations revealed that almost all galaxies appeared to be moving away from each other, and that the redshift of a galaxy was directly proportional to the distance of the galaxy from Earth. This was a major breakthrough. It meant that the universe must be expanding. Hubble announced his finding in 1929, and following its publication, it became supporting evidence for Lemaitre's expanding universe theory, which would become known as the Big Bang. Hubble's initial measurement of the rate of the expansion of the universe, which would become known as the Hubble constant, was roughly 160 kilometers per second per million light years. That's about 500 kilometers per second per megaparsec. However, that number was not quite accurate, and even Hubble himself worked to refine it over his career. Since then, the Hubble constant has become a fundamental value in cosmology. We've used it to establish the age and the size of the universe, and those numbers are important for many, if not all other cosmological calculations. To narrow in on the most precise value for the Hubble constant, astronomers have used two primary methods. But something about this value isn't adding up. One way astronomers measure the Hubble constant is through additional observations of redshift. In other words, the same way Hubble made his initial discoveries. Known as the cosmic distance ladder, or late universe method, it measures the expansion as we see it now, billions of years after the Big Bang. The more examples of distant redshift that we're able to get, the more accurate the measurement should become. Over the years, this has refined the Hubble constant to approximately 73.5 kilometers per second per megaparsec, quite a bit less than Hubble's original value. The other way to measure the Hubble constant is through the early universe method, a newer technique that estimates the expansion by rewinding the clock back to the start. This relies on images of the cosmic microwave background, or CMB, an ancient microwave radiation, which is, essentially, a snapshot of the universe from about 380,000 years after the Big Bang. This cosmic microwave remnant had been predicted in 1948 by Ralph Alpher and Robert Herman. Arno Penzias and Robert Wilson detected its presence in the 1960s, winning the Nobel Prize for their work. But it wasn't until later that we got a detailed enough image to predict the age of the universe with precision. In 2003, the Wilkinson Microwave Anisotropy Probe, or WMAP, released an all-sky map that showed the early universe, a time before there were even any stars. You can think of it like this. Imagine you come from the scene of an explosion that has already happened. You see fragments strewn all over the place, and you can't make out what the original object used to look like. But then someone hands you a snapshot of just after the explosion began. I bet now you could trace each piece back where it belonged in the original image. This is similar to how astronomers use the cosmic microwave radiation to trace our present universe back to just after the Big Bang. Most recently, in 2013, the European Space Agency's Planck cosmology probe was able to capture an even more detailed all-sky image of the background radiation, showing subtle fluctuations in temperature that would eventually ripple out to create dark matter webs, forming clusters of galaxies and voids across the universe. When astronomers take the image of the CMB and fast forward it to the present day, it's like pressing play on the video of the explosion. They get a predicted Hubble constant of about 67.4 kilometers per second per megaparsec. But you might notice, this value is considerably smaller than the Hubble constant we've observed through redshift, which is a problem. I really can't stress enough how the expansion of the universe has become a pillar of our standard model of cosmology. The Hubble constant ties into our most fundamental physics, from Einstein's theory of general relativity to the idea that the universe evolved from a dense, hot, early state known as the Big Bang. Otherwise known as the lambda-cold dark matter model, it emerged in the late 1990s and has seemed to work beautifully ever since. An important feature of this model is that scientists expected gravity to slow the expansion over time, but instead, they've actually found it's now speeding up. Thankfully, this didn't break the model. Something seems to be pushing space apart faster and faster, and we believe that something is dark energy. As the universe grows, dark energy's effect becomes stronger, causing galaxies to move away faster and making the Hubble constant, the rate of our universe's expansion, increase over time. Both methods of calculating the Hubble constant are meant to give us the current rate of expansion, so it's not this acceleration that's making the results differ. But how can we have one unified cosmological model with two different values for such a fundamental rate? This discrepancy has become known as the Hubble tension, not because it represents an actual tension force, but instead, probably because of all the atmosphere it creates at cosmologists' dinner parties. And to be honest, I get it. It could mean we've got our entire cosmological model wrong. It was thought that as more accurate data was collected, these two values would converge on one agreed value Hubble constant. But therein lies the problem. As we've gotten more recent, independent measurements of the redshift, the number isn't converging. Instead, the gap is being reinforced. One independent measurement came from mega-maser hosting galaxies. These have certain molecules like water vapor that can amplify microwave radiation near a black hole at the center of a galaxy. This can create a maser, which is like a laser but with microwave radiation instead of visible light. Megamasers are extremely powerful, and their microwave emissions can be mapped precisely using telescopes. That means they can be used to measure the mass of the black hole and give a very accurate geometric distance to their host galaxy, allowing us to calculate the Hubble constant with, presumably, a very accurate distance measurement. In 2020, astronomer D.W. Pesce and others used this method to measure a Hubble constant of 73.9 kilometers per second per megaparsec with 95 to 99% confidence. In other words, they were very sure. And in late 2024, another investigation by Daniel Skolnick, Adam G. Rees, and others resulted in a similarly shocking value. They used data from the Dark Energy Spectroscopic Instrument to study 12 different Type 1a supernovae that were dotted across the Coma Galaxy cluster around 320 million light-years away. What they found was a Hubble constant of 76.5 kilometers per second per megaparsec. Most recently, in 2025, researchers from the Inter-University Center for Astronomy and Astrophysics in India used mirror variable stars in our galaxy as anchors to measure the distance of mirror variables in faraway galaxies, a similar method to the original way of using Cepheid variables. They found a Hubble constant value of 73 kilometers per second per megaparsec. All of these measurements roughly agree, but fall far outside of the error range of the Planck measurements based on the CMB radiation. So something seems to be missing from our understanding of the universe. Astronomers, including two who worked on the DESI investigation, have been ringing the alarm bells. The paper's lead author, Skolnick, a professor of physics at Duke University, said our model of cosmology might be broken, and noted that the Hubble tension is feeling more like a Hubble crisis. Without resolution, the model we use to interpret the universe rests on shaky grounds. Everything from when galaxies formed to how clusters evolve, and even predictions of the cosmic future hang in the balance. If the Hubble constant turns out to be the lower value calculated from background microwave radiation, then we live in a 13.8 billion year old universe that will likely go on expanding forever, a steady, predictable future with constant dark energy. But if the Hubble constant is the higher value observed from redshift, then our universe may be expanding faster than the current model predicts, and things may be weirder than we thought. If that were the case, then our universe may be younger, something like 12 to 13 billion years old. And it may mean that we're missing something fundamental in our understanding of the early universe, dark energy, or relativity. Some scientists have proposed that radical adjustments may be needed to reconcile the Hubble tension. These proposed adjustments have included things like decaying dark matter or dark energy that varies over time, and scientists have even explored the idea of modifying the dark energy equation of state, representing what could be a change to general relativity itself, something that may force us to reevaluate our entire understanding of not just the cosmos, but also our very understanding of physics. But another recent idea has been gaining traction, one that could save our model of cosmology without needing to rewrite physics. And all it needs to work is a little spin. No, really. The 2025 paper suggests that perhaps we've missed a very slow rotation or spin of the universe. Published by Balázs András Zigeti, István Zapudi, Imre Ferencz-Barna, and Gergely Gábor Manifoldi, the idea is that a very slow universal rotation once every 500 billion years would be slow enough to go undetected, but significant enough to affect how space has expanded over time. In fact, their preliminary calculations show that this slow spin could validate both values we have for the Hubble constant. When spin is introduced into the model, it predicts an early universe with a lower rate of expansion, like we get from the CMB calculations, and it also predicts a present universe with the higher rate of expansion, like we get from redshift measurements. These are exciting initial results. Zapudi, one of the idea's authors from the University of Hawaii, paraphrased the Greek philosopher Heraclitus of Ephesus when explaining the hypothesis, who said panta rei, meaning everything moves. And indeed, with how promising the initial results are, it may be true, entire universe and all. Though the authors were clear that this is just a preliminary calculation focused only on the Hubble constant. The next step towards solidifying this idea will be more complex models and simulations to check the hypothesis against other observations. I believe this idea is a reminder that there's still a lot to learn about our universe, but it's far too soon to think about throwing out our entire model of cosmic evolution, especially when we may be just on the brink of understanding the missing piece. And even if we can keep our cosmological model, it would still mean a new rotating variant of it, one where cosmic parameters and values shift to accommodate our new reality. And this idea has one other major perk. It doesn't violate any known laws of physics. Besides, I quite like the idea that not only is our planet spinning and our solar system rotating, but so too are the Milky Way galaxy and our entire universe. Is the universe inescapable? If we were to conquer the limitations of light speed and were to travel to space's furthest edge, what might we find? Just more space? Infinite planets and planetary systems? Or would we somehow come back to where we started? Amazingly, according to scientists, all of these are possible, but which one is correct comes down to the nature of that unseen world all around us. I'm Alex McColgan and you're watching Astrum. Join me today as we continue our series exploring the unseen world of 4D space and discuss possible answers to the question, what is the shape of the universe itself? But first, let's begin by talking about infinity. You are likely already familiar with infinity. In maths, it is the concept of a number so large it cannot possibly be beaten. Of course, no such number exists. For any number you can name, I could come up with a number that is at least one larger than it. But in a way, that's sort of the point. In infinity, there is always another number. And when it comes to our universe, we have so far discovered no edges. There may always be another star or planet. An infinite universe is a little mind-boggling for us. We live in a very finite world with edges and endings, so the idea that there might be literally infinite more planets out there is a little bewildering. However, as we develop more and more powerful telescopes and push back the darkness further and further at the edges of what we can observe in our universe, all we are finding is that even the darkest patches of the night sky are turning out to be brimming with stars. So increasingly, an infinite universe might be something we are forced to contemplate. But that is not to say that just because the universe is infinite, there are not a finite number of things in it. That may sound a little counterintuitive, but let me show you what I mean. Believe it or not, there are different kinds of infinity when it comes to our universe. 3 possible scenarios could be true: a flat universe, a spherical one, or a hyperbolic universe. Allow me to explain. In a flat universe, if we were to form a grid to broadly represent reality, everything would seem fairly standard. All the lines would either be parallel to each other or perpendicular. An infinite universe of this variety would simply extend outwards in all directions forever and ever. This is a little boring, so I won't spend too much time on it. However, this is a lot like we perceive the universe to be. For the most part, all lines of direction appear straight to us. We can distinctly see the planets and stars around us, and we notice no real curving or warping. However, this is not the only way that the lines can be drawn. Consider for a moment a black hole. You may immediately notice the strange rings that appear to run around its equator, as well as across the top of it and along the bottom. This is something of an illusion. There are no rings across the top or bottom of this black hole. What you are seeing is the equatorial ring that's on the other side of the black hole. However, due to the powerful gravity of the black hole, the light that is hitting it is not bouncing off upwards or downwards into space. Instead, the rays are curving towards us as the black hole's gravity pulls them in. You are seeing the top and bottom of the ring at the same time. Light being bent by gravity. What do I mean by that? Actually, this is an excellent example of our second kind of universe. In a flat universe, all the lines that make up reality are fairly straight. But what if we were to come up with a rule? All the lines must instead curve towards each other. There is only one way such a universe could be drawn, and that is in a sphere. Consider trying to draw 2 parallel lines on a sphere. You might start off well, but will quickly realize that your task is impossible. All lines would converge towards each other, intersecting at least twice as they return back to where they started. What would a universe that was based on these kind of lines look like? Essentially, rather than going in the straight line you thought you were going in, you actually would be traveling in a massive curve. It's a bit like those computer games where you travel off one end of the screen only to reappear from the other side. In a spherical universe, you could travel infinitely, but ultimately you would only end up arriving back where you started. With a powerful enough telescope, and if light were to travel a whole lot faster all of a sudden, it would be possible to look at the back of your own head. This kind of universe contains a finite amount of things, but it appears infinite because you just keep bumping into the same things infinite times. Thanks to objects like black holes and powerful stars, we do indeed have evidence that our reality sometimes is a curved spherical one, at least near large bodies of mass. The inside of a black hole's event horizon is this kind of infinite space. No matter what path you take, you can never get out of it. However, let's consider our last example, the hyperbolic universe. This one is the hardest to visualize, but the idea is simple. Instead of having all lines remain parallel or move towards each other, every line must move away from everything. Drawing this is inherently tricky because everything keeps getting wider exponentially. The only way you can do that is to either buckle your nice flat disk until it becomes something like this, or warp what you are seeing like this. All of the objects in this image are squares. However, they are squares that are obeying our rule that all their lines must be diverging away from each other. This leads to the very strange situation where you can have 5 squares all meeting up at a corner instead of the usual 3 that is possible in normal 2D space. Alright, this seems a little confusing. What does it mean if space is hyperbolic? Well, let's consider what it is we are curving around. You might have noticed when we talked about our spherical shape that there must be something we are curving around. That direction of curvature is in regards to time. Imagine, if you will, a series of timelines. We go a little more in depth with the interplay between space and time in my last video, which I would really recommend you check out. But for now, just remember for this model that objects in time move forward along their timelines in the direction of up, or the future. If they move left or right, they are moving through space, getting closer to each other. If we introduce a large mass into this model, it warps the timelines. Now, if you were a small object traveling along one of those arrows that got too close to the mass, suddenly your path of travel no longer goes directly up towards the future. It pulls you left or right towards the mass. There are several reasons for this, but the essential thing to recognize here is that now your straight path towards the future pulls you in towards the planet, so you'll have to accelerate away from it just to stay on a straight path. In a nutshell, you are experiencing gravitational pull. Even the planet is affected by this. The atoms on either side of it are squeezed towards the center of mass, as if it were being forced down a narrow tube by giant invisible hands. Let's get back to hyperbolic space. In this model, the opposite thing is happening. All lines are moving away from each other. We could represent this by curving space and letting our timelines be straight, which is nice because it captures the idea that from your perspective, your time is always ticking forward normally. But let's warp this slightly so that space is flat. It's all a matter of perspective after all. Here, parallel lines are also impossible, but this time, rather than converging, all parallel lines diverge more and more. Everything moves further and further apart. Why does that sound familiar? It is because that is what the universe is doing. This is not noticeable within a galaxy, where there is enough mass and gravity to keep everything together. However, from what we can see of the universe as a whole, every galaxy is moving away from every other galaxy. Scientists try to explain that with dark energy, but maybe all that is happening is that the universe is just naturally hyperbolic in its shape. So what would that mean if the universe really was hyperbolic? It would mean that the universe was really infinite. The flat space we looked at was infinite. For each light year you traveled out, you discover another light year's worth of space. However, with hyperbolic space, you discover more than another light year's worth of space. It's like opening infinite doors, except inside each door are 2 new ones. The possibilities would be far more endless, far more infinite than in just regular flat space models. But also, it means that given enough time, the rest of the universe would drift away from us until our galaxy was all that was left. Scientists have looked across the universe, however, have not noticed this hyperbolic space in action. In fact, things all look pretty flat, so perhaps flat space is the correct answer. Yet, this still leaves room to me for hyperbolic space to be the default. After all, if matter is curving space towards it, and the universe appears flat, it would make sense that the universe was curved in the inverse, at least to some degree. Perhaps all three models are true. Perhaps the universe is by default hyperbolic, but mass brings it together in such a way that it perfectly offsets the inverse curves of the universe to the point where everything appears flat. There certainly seems to be some evidence that this is the case, but it's very difficult to know for sure. Which model do you think is correct? Or maybe you feel that we do not live in an infinite universe at all? Please leave a comment down below to tell me what you think. But for now, just remember, the unseen world might be a lot more influential on our universe than we are currently aware of. When the James Webb Space Telescope finally saw the edges of the universe, we knew we had a problem. Webb was able to resolve light emitted from stars 13 billion years ago, helping us to peer back in time to some of the universe's earliest moments. But what we saw was not a sparsely populated proto-universe, where matter was only just starting to coalesce into the first, tiny, intermittent galaxies here and there. The early universe was a bustling place. It had galaxies. Too many of them. They were too bright, and the black holes we started to spot in their hearts had grown too big too quickly. Some began to proclaim that our models were wrong and cosmology was in crisis. And while some of these problems have begun to alleviate as better data came in, other problems simply became more prominent. But in a strange twist, one of the most resilient mysteries in all of this might be about to unravel thanks to a small black hole with an impossibly big appetite. Its name is Lid 568, and we've just seen it breaking the Eddington limit, consuming matter faster than it should be able to, and it might just be the key to everything. I'm Alex McColgan, and you're watching Astrum. Join me today as we explore Lid 568, the Eddington limit, and its groundbreaking implications on cosmology. A black hole breaking physics? By now, I really shouldn't be surprised. It takes time to cook up a galaxy. Interstellar gas and dust need time to subtly come together under gravity until a critical mass is reached and stars begin to ignite. These stars live and die, and from their deaths, new stars are formed. This too takes time. Cosmologists have observed our universe and, based on what they saw, created models for how old our universe is and how quickly galaxies form, which is why the James Webb Space Telescope data caused such a crisis. Things were not as the models predicted. Fortunately, some of those problems proved solvable in the months after the data was released. For example, the brightness of the galaxies we could see through Webb. This brightness implied that there were far too many stars present in those galaxies. So many stars should have taken much longer to form, and yet there they were, fuzzy red dots at the edge of Webb's resolution. However, scientists at the University of Texas studying Webb's Cosmic Evolution Early Release Survey realized there could be another explanation for all that excess light, and counterintuitively, that explanation was black holes. If we work under the assumption that there were massive black holes in these galaxies rapidly consuming cosmic gas, then the intense friction given off by these hungry leviathans as they ate created an excess of light in their accretion disks. This explains why galaxies overall seemed brighter and were throwing off our estimates. Once you add these shining black holes, you don't need so many stars. The mass of each problematic galaxy dropped, and everything fell back into line with the cosmological model. Problem solved. This reinforced how important black holes are to our understanding of the early universe, which was in and of itself a problem, because the black holes themselves broke our models too. In particular, cosmologists struggled with the thorny question of how they'd come to be. For small black holes, known as stellar black holes, there was no issue. Stellar black holes have masses a few to 100 times that of our Sun, and we understand very well how they are formed. They are the collapsed remnants of a sufficiently massive star, and there would have been time for such black holes to form in the early universe. But scientists were struggling with the supermassive black holes, with masses tens of thousands to billions of times that of our Sun, which tend to lurk at the central point of galaxies. And due to something called the Eddington limit, there just shouldn't have been time for these kinds of black holes to have formed where and when Webb saw them. And yet, there they were, and they were numerous. Stellar black holes can grow as time goes on, provided you funnel more mass into them. But how quickly? In 1920, an English astronomer and physicist called Arthur Eddington formulated the idea that there was a limit to how quickly either a star or a black hole could grow. This was because photons carry momentum, a tiny amount, true, but enough to exert a push. This is what pushes solar sails on certain hypothetical spaceship designs, that tiny amount of momentum imparted by photons. For mass to enter into a star, it has to push against a constant stream of photons that are radiating outward, and at a certain level of brightness, not even gravity is strong enough to pull against the flow. This is called the Eddington limit, and stars that brush against its boundaries, such as Wolf-Rayet stars, bright stars at least 20 times more massive than the Sun, emanating powerful stellar winds, are just the slightest nudge away from blowing themselves apart. For black holes, you might think this would be less of a problem. Isn't the whole point of black holes that they don't radiate any light? But their accretion disks are a different story. As we discussed earlier, accretion disks around supermassive black holes can be incredibly bright, particularly around supermassive black holes, sometimes dwarfing the brightness of the stars in the galaxy they reside in. With brightness comes resistance to gravity, and black holes have to obey the Eddington limit too. So even though, given enough time and mass, stellar black holes could theoretically grow into supermassive black holes, it doesn't seem plausible that this actually explains all the supermassive black holes we see in the early universe. Simulations have been run, and although it is technically possible to grow a stellar black hole into a supermassive black hole in that time frame, it would require those black holes to be feeding at near the Eddington limit non-stop since their birth, which just doesn't happen. Black holes in real life often run out of mass nearby and need to wait to run into more, or for more to come to them. To further complicate the matter, we're not completely sure that supermassive black holes are the grown-up version of stellar black holes in the first place. Although it seems like common sense to assume so, scientists have been confused at the lack of the intermediate stage of black holes observable in our universe. To be frank, they've not cited any, at least none for sure. Supermassive black holes are common at the center of galaxies, and there are thought to be 100 million stellar black holes in our Milky Way alone, based on the number we've seen. But intermediate black holes are suspiciously lacking, with only a handful of potential candidates. You would think we'd see a lot more. Struggling for certainty, scientists began to hypothesize that supermassive black holes were instead born in some other way. Many cosmologists have been exploring the idea that because everything was much closer together in the early universe, things might have been dense enough that interstellar dust itself could conceivably have collapsed to form a black hole directly, skipping the star step altogether. If this is true, and there is some evidence to support the theory, then perhaps supermassive black holes were once capable of simply being born that size, or near it, right from the offset, even if such a thing is no longer possible in our more spread out universe today. But this is by no means certain. But then, Lid 568 came onto the scene, and the pendulum swung the other way again. Lid 568 is a very distant black hole, between 12.1 and 12.3 billion light years away. It's so far away from us that we can't see it at all using visible light. The expansion of the universe has redshifted it all into infrared ranges. But even its infrared emissions were too dim to be picked up by heavy hitters like Hubble alone. It took the Chandra Cosmos Legacy Survey's combined telescopes and the incredible resolution of the James Webb Space Telescope to see it at all. Even then, Lid 568's whole galaxy is a little more than a faint, red and compact dot. But the light emissions from this red dot are revealing. X-rays given off by Lid 568's accretion disk reveal that it was actively consuming matter in its galaxy's heart in a way that no one expected. You see, Lid 568 crucially breaks the Eddington limit, and not just by a little, it's 40 times over the accretion speed limit. It's well on its way to having its license revoked. How is this possible? It turns out that breaking the Eddington limit is, in fact, possible, but only for short bursts or in sneaky ways. For example, jets can help you get around the Eddington limit if all your photons are being blasted off in a single concentrated direction. All the other directions can eat to their heart's content, with no photon feedback getting in the way of a good meal. There are other possibilities. While Eddington's limit says that once the brightness of the accretion disk becomes too high, all the black hole's food will be blown away, there is a period of time before this happens where a greedy black hole can snatch at the escaping matter and potentially enter super Eddington territory. Like an overeager diner, it might pay for it later, but for a short burst, that level of accretion can occur. If this is true, it might just explain how supermassive black holes in the early universe came to exist. And certainly, Lid 568 exists, and is the clearest example to date of a black hole accreting this quickly. That demands our consideration, much like the impossible supermassive black holes themselves. They are there. It's now our job to attempt to understand how that's possible. So, mysteries remain. If Lid 568 is accreting matter past the Eddington limit, it proves such a thing is possible. But what of the other strange things Webb saw? Where are the intermediate black holes that stellar black holes ought to grow into, on their way to becoming supermassive? Why are there so many galaxies in the early universe, more than our models should allow? Do direct collapse black holes, ones formed from the cosmic dust itself with no stellar intervening step, really exist? Our models might be on the right track, but something is missing or incomplete. Black holes exert a phenomenal influence on our universe, and there are secrets surrounding them that they guard jealously. But as powerful as the James Webb Space Telescope is, it has not allowed us to crack this mystery. Not yet. But then, perhaps we ought to be pacing ourselves. Thanks to our telescopes, we have seen billions of trillions of stars, and that's a lot of data. Accrete too much information all at once, and it might prove difficult to absorb it all. So says Eddington, and his rule is never to be broken, except, of course, when it is. We often think of black holes as destroyers. They suck everything within their reach into them and give nothing back. They are the end, the final destruction of the universe. And yet, what if I said to you that they might actually prove to be our salvation? Black holes might provide the answer to traveling faster than the speed of light
and solving the energy crisis in ways we couldn't have even imagined until recently. And, as by now I have come to expect, they do so by messing with the fabric of reality itself, and by completely countering my expectations of physics. Perhaps we have been thinking about black holes all wrong. I'm Alex McColgan, and you're watching Astrum. Join me again for the 5th video in my series about black holes, where once again my mind has been blown by the incredible potential and implications of these very real objects in our universe. I've talked before about the formation of black holes in this series, including aspects about their event horizons, how they are created, and how they might possibly end. But to understand how a black hole ignores the usual limitations on faster than light travel and does so in a way that you can benefit from it without having to go inside a black hole's event horizon, and how it produces near limitless energy at the same time, then we are going to have to understand more about the features of black holes than we've covered so far. So, a quick recap: what is a black hole? In its simplest form, a black hole is an object in space that is so massive and so dense that the gravity it creates is too powerful for anything to escape it. We are familiar with the iconic black spherical zone that surrounds a black hole. This is the black hole's event horizon. This sphere is the demarcation point between escapable gravity and inescapable gravity. Because the gravitational pull increases the closer you get to a black hole, once you go beyond the event horizon, nothing, not even light, can travel fast enough to get away again. Beyond that though, it's actually quite difficult to say much about a black hole's features at all. Precisely because of the event horizon, we cannot see what the inside of a black hole looks like. In fact, there are only 3 things we can say about black holes with any degree of certainty. They have mass, they have charge, and they have angular momentum. You might wonder how we know these things about black holes, given that no light can leave them to tell us about them. The key to these 3 characteristics is that all 3 of them represent aspects of the black hole that can be felt outside the black hole's event horizon. Charge, for instance, works the same way around a black hole as it does around any other charged object. That is to say, if a black hole is charged, then it will attract objects that have different charge to it and repel objects that share its charge. Think of it like a giant magnet, pushing and pulling on the universe around it. Scientists can track objects that approach a black hole, and by seeing how quickly certain objects known to have a charge move towards it, scientists can predict the charge of the black hole itself. Interplaying with this is mass. The mass of a black hole can also be felt outside the sphere of the event horizon. In fact, it is the main creator of the event horizon in the first place. This is because mass creates gravity and does so in a linear fashion in accordance with the same principles you might find in Gauss's law, a theorem about electromagnetism, albeit with a gravitational analog. So, it's possible too to calculate the mass of an object by seeing how far away objects are before they start to accelerate towards it, and how quickly they accelerate. Although obviously, you need to factor in charge at the same time, or your results might get skewed. Finally, angular momentum, or spin. It is possible to detect the spin of a large mass object, and we are going to dive into the how in just a bit. For now, let's just accept it as a given and recognize that black holes are certainly very high mass objects. There are varying sizes of black holes in existence. The smallest, known as micro black holes, have a mass that's comparable to that of our moon, or 7.35 times 10 to the power 22 kilograms. They fit all this into a space that's just 0.2 millimeters in diameter, which is incredible. It really gives you a sense of how dense a black hole can be, something thinner in size than a human hair, packing the mass of the moon. And that's just the smallest ones. Stellar black holes have a mass equal to 10 times our Sun, and have a diameter equal to 60 kilometers. Intermediate black holes are the mass of 1,000 suns, and fit all of that into a diameter of 2,000 kilometers, which is still much smaller than the Earth. it is the largest black holes that really dwarf us, with masses between 100,000 to 10 billion times the mass of the Sun, and sizes ranging from 0.001 to 400 astronomical units, an astronomical unit being the distance from the Earth to the Sun. But other than those three features, there are in theory no other differences between them. If you put two black holes in the same room and made sure they had the same mass, charge and spin, it would be impossible to tell them apart. However, these three features are enough to have some interesting effects on the area of space outside a black hole. Traveling inside a black hole is impossible. Space and time break down past the event horizon, but we think we know a few things that must exist inside one. Beating in the heart of a black hole, there is thought to lie the singularity. In truth, this actually is the black hole. When we were discussing diameters earlier, that is just the diameter of the event horizon. Again, we are not certain what a black hole actually looks like because light can never escape it. In a space that is infinitely small, there is a point where all the mass of the black hole is packed so that it is infinitely dense. For the simplest models of black holes, the ones that do not spin, this is a single point. In a rotating black hole, this is more like a little spinning ring, otherwise it would be difficult to define spin for a point that has no volume. Our current physics get very strange around such a black hole. If ideal paths are travelled around this point, it becomes mathematically possible to do some very strange things, like meet up with your own past. This has some disturbing implications for causality and gets into time travel paradoxes like the grandfather paradox. So that probably only shows for certain that our ideas about singularities are not quite right yet. Because the singularity is so small, it'll take the successful merging of quantum theory and general relativity theory to properly explain what is going on inside a black hole, and we have not yet managed to do this. It may one day turn out that singularities do not exist in the hearts of black holes at all, but this is the extent of our knowledge so far. Well, whatever it is that lies inside a black hole, it powers our faster-than-light engine, because like most objects in the universe, it spins. And oh, does it spin! As we travel out from the center of the black hole, we pass through the event horizon with little fanfare. The event horizon actually cannot be detected locally, although a person outside the black hole might watch you slow down to a complete stop as you travel through it. From your perspective, it actually might seem like time is flowing normally. Normally, that is, until the universe outside the black hole runs its course in an instant, because time outside the black hole is traveling so fast compared to you. This is the essence of relativity, and we talk about it in another of my videos, which you can look at here. In fact, the only evidence you might have that you've passed the event horizon at all is because of something that exists just outside it, the photon sphere. In a zone just outside the event horizon, there exists a point in space where if a photon enters it at just the right angle, it will enter a perfect orbit around the black hole in much the same way the moon perfectly orbits the Earth. This infinitesimally thin zone is known as the photon sphere, and given the number of photons that have flown past black holes in all the millions of years they have existed, it is probably filled with photons. It is quite possible that you would be instantly fried as you pass through this point. However, it is just outside here that we find the zone that interests us, the ergosphere. This is the zone around a black hole where we can most easily detect its spin, and this is because, in this zone, it is impossible for us not to move. You see, mass affects space. We see this in the curving effect of gravity on the travel of objects through that region of space. However, it might be more accurate to say that mass drags on the space around it. As it moves through space, it brings a little bit of that space along with it for the ride. And when an object as massive as a black hole spins, there is an effect known as frame dragging. To put it simply, reality around the black hole begins to spin in a whirlpool that cannot be fought against. Much like a real whirlpool, anything caught within the ergosphere is spun around the black hole, because the frame of reference it sits in is being pulled. Sort of like how a person moves because they are standing on a moving walkway. The greater the spin of the massive object, the faster this happens. And in the ergosphere, this can occur at a speed so fast that by the event horizon, space is moving faster than the speed of light. You would need to travel faster than the speed of light in the opposite direction just to stay at a relative standstill from the point of view of the outside observer, which of course you cannot do. But isn't this against the laws of physics? Doesn't Einstein say that nothing can travel faster than the speed of light? The answer to that is yes, but black holes have found an interesting loophole. You see, this rule only applies locally. Right where you are, in your frame of reference, nothing can go faster than the speed of light. But thanks to relativity, it is possible for frames of reference to move away from each other so fast that objects in them appear to be breaking this light barrier from your point of view. But if you move next to them and entered their frame of reference, they would seem to slow down and would start obeying the laws of physics again. It's a really weird effect, but frame dragging is an actual thing. It is by measuring frame dragging that scientists can learn the spin of a black hole. However, according to a man called Roger Penrose, there may even be a way of exploiting it. If you were to send a rocket into this section of the ergosphere, the rocket would speed up due to being caught in the whirlpool of reality. Once it had gained enough speed, it could then fire a propellant in such a direction that it pushed itself out of the whirlpool again, but now traveling at a much faster speed. This method, named the Penrose process, could hypothetically net you energy equal to about 20% of the mass of your rocket. Now, that might not sound like much, but remember, according to Einstein's E equals mc squared, your 20% mass would produce energy equal to itself times by 299,792,458 squared. That's a lot of energy. So to harness this colossal kinetic energy, all you would need to do is travel to the nearest black hole, which is roughly 3,000 light years from us, and enter its ergosphere with a rocket capable of surviving the intense gravitational forces there. Ideally, you would need to find one that was not surrounded by an accretion disk, because those get up to temperatures of millions of degrees, as they are swung around at near light speeds and melt from solids down to gas and plasma. But you get the idea. Easy. Okay, maybe this is a little impractical for us, but the implications for faster than light travel that black holes demonstrate through frame dragging might just offer us the key to one day beat the light barrier for real. Not by going faster than light ourselves, but by somehow convincing the frame of reference we are in to travel at those faster speeds, just like they do around a black hole. Of course, if this requires the energy of a black hole to accomplish, we might be out of luck for now, but it's an incredible glimpse into what is possible, and scientists are already looking into the power of frame dragging for future travel. But maybe that's a topic for another video. Either way, this all just highlights once again how our universe really is very different from what we might have ever imagined. Movement through space is inevitable. You might not feel it, but right now you're sitting on a planet that is spinning on its axis, moving you at up to 1,600 kilometers per hour depending on your latitude. The Earth circles the Sun. The Sun moves through the Milky Way. The Milky Way moves through the local group of galaxies. And the local group moves through our local supercluster. And even that supercluster of galaxies is in motion, heading towards the Shapley supercluster, where scientists believe that there is a particularly large concentration of galaxies. I hope all this motion isn't making you too dizzy. But on the grandest scales of our universe, something strange is happening. Scientists have begun to realize that there is not enough mass in the Shapley supercluster to pull us towards it at the rate that we see. About 50% of the cause of that motion is unaccounted for. In 2017, researchers discovered a possible source for the rest of that motion. But it's not something pulling us, it's something pushing. I'm Alex McColgan and you're watching Astrum. Join with me today as we explore the evidence for the region of space known as the dipole repeller and try to understand how, in a universe filled with gravity, something can push us instead of pull. Let's start with a little context. It's taken a long time for astronomers to recognize that this motion was taking place. To understand that we were moving, scientists first had to make a map of the regions of space around us. And although we as a species have been mapping the stars since the beginnings of civilization, it was only thanks to Mr. Hubble in 1924 that we proved there are actually stars in other galaxies outside the Milky Way. Before then, although astronomers had seen fuzzy little clusters of light in the night sky that we now know to be galaxies, the common wisdom was that these were gas cloud spiral nebulae within the Milky Way, not something that existed beyond it. Hubble noticed several Cepheid stars, a type of variable star with a cycle of variation closely linked to their luminosity, within one such spiral nebula, and used the fact that this luminosity was very predictable based on distance to calculate very precisely how far away they were. Surprising many, he proved that they do exist beyond the Milky Way. Since then, astronomers have been scrambling to catch up with the new reality of galaxies and superclusters, and set about mapping the locations and distances to every galaxy they could find. Hubble had been studying Andromeda, our closest neighbouring major galaxy, but there were others. By the 1970s, Stephen Gregory, Lard Thompson, and William Tift definitively proved that galaxies didn't just float randomly in space, but converged into superclusters, large filamentary or sheet-like structures that exist between large bubbles of void. They mapped the first supercluster, the Coma supercluster, which covered a region of space 100 million light-years across. A whopping 95% of all galaxies are found in these superstructures. It wasn't until 2014 that our own supercluster, the Laniakea supercluster, was fully mapped. You might be surprised to hear it happened in that order. After all, wouldn't common sense say it's easier to map regions of space closer to us rather than ones further away? Why was it only nearly a century after the discovery of other galaxies existing, and 40 years after mapping the first supercluster, that we finally turned to our own? The answer is that mapping the local regions of space around us is surprisingly challenging, and it's all because of the Milky Way getting in the Milky Way. The Milky Way is full of gas and dust, and these regions are so difficult to penetrate that we can't really see beyond them. Towards the center of the Milky Way, this effect gets so bad that scientists have dubbed the whole area the zone of avoidance. Very little light gets through it. Not being able to see in this area is particularly relevant to our current discussion for reasons we'll get to later. In contrast to our local area, distant galaxies are easier to study, as all you have to do is point your telescope at a single point in the night sky and let it drink in the light. Mapping the area around us requires looking at every point in the night sky. It's proved quite difficult, although astronomers are now getting a better handle on it. Thanks to their efforts in looking at thousands of galaxies in our galactic neighborhood, and by studying galaxies' peculiar motion, or their motion relative to the cosmic background radiation that ignores the expansion of the universe, scientists have been able to group gravitationally bound galaxies into superclusters. At the center of our Laniakea supercluster lies a point known as the Great Attractor, an area 150 to 250 million light-years away from us, that we, in the Milky Way, are slowly drifting towards. Sadly, the Great Attractor lies within the zone of avoidance, so it's tricky to see clearly what lies there. To confound things further, the Laniakea supercluster was also found to be moving. It travels towards another supercluster known as the Shapley supercluster, taking us along with it. At the center of this supercluster lies the Shapley attractor, which also is believed to be incredibly dense in terms of mass. But frustratingly, this second attractor also lies in the zone of avoidance, making it difficult to see exactly what's going on over there too. Thankfully, as X-ray and infrared telescopes improved, it became possible to take a better look at these two attractors. But this is where the mystery begins. What mass is there is not quite massive enough to account for our apparent motion in that direction, which is why a team of researchers from the University of Hawaii published an article in Nature to attempt to explain this discrepancy. The team was made up of Yehuda Hoffman, Daniel Homerede, R. Brent Tully, and Helene M. Courtois. Together they created a new kind of map of the local universe around us. This time, instead of simply noting galaxies' positions, they highlighted their motions instead. This allowed them to create a map of flow lines, which, after mathematical analysis, allowed them to make assumptions about the locations of masses in our nearby superclusters. Their results were surprising. A lot of our local mass is moving towards the Shapley supercluster, which is what you would expect. But they also found a lot of mass is moving away from another specific region in space. They call this mystery patch of space the dipole repeller. Together, the dipole repeller and the Shapley attractor both contribute about 50% to our motion, working together in tandem, hence the name dipole. But how? Gravity is a force that, so far as we have observed, only pulls. What lies in this region of space that allows a push to happen? Could it be a strange collection of white holes? The theoretical opposite of black holes that we've talked about in videos before? Or perhaps some source of anti-gravity? Not quite. The answer is nothing. The dipole repeller is a void, a bubble about 100 million light years across that does not contain many, if any, major galaxies. It's one of the bubbles that exist between the filaments of the universe's structures. But interestingly, our galaxy's current motion lines up much more satisfyingly with the push from this region than it does from the pull of the Shapley attractor, which is a compelling argument in this theory's favor. So, how does nothing push? The answer is actually that this could be a pseudo-force more than it is a real one. Imagine a universe where all the galaxies were spaced equally. While the gravity of galaxies above would pull you, the gravity of galaxies below you would do the same. So would the pull of galaxies to your left and to your right. In this way, the varying forces of all these gravities would balance each other, leaving you to not really travel in any direction. You'd be in a perfect equilibrium. But what would happen if we removed the galaxies from one of these directions? What would happen if we added a void? Well, then the scales would tip. There would be one direction that no longer pulled you, leaving the opposite direction's pull to act on you unimpeded. As a result, you would move away from the void as if it were pushing you. Everything near a void will thus move away from it, making it seem to have a repelling gravitational force. It is something of an optical illusion. There is another explanation for why a void space might push you, which might work in tandem with the pseudo-force. The universe is expanding, and that expansion shows no sign of slowing down. In fact, it seems to be speeding up. However, this expansion is counteracted by gravity, and in areas where there is more gravity, less expansion seems to take place. Stars aren't just being pushed away from each other, they're also being pulled together. Conversely, in a void, there is nothing to contain this rampant expansion. As a result, void spaces literally will swell compared to their supercluster counterparts. It might be done by warping the fabric of reality, but this also achieves a sort of push. Since 2017, not much more has come to light about the existence of the dipole repeller. As this is still an expanding field of research, there's some debate about whether it's really there, or how influential it might be on our galaxy's current motion. It is difficult to observe due to the Milky Way's obscuring effect, and there is always a challenge inherent in trying to spot the absence of a thing rather than its presence. However, Tully and his fellow researchers hope that with the aid of future ultra-sensitive surveys in multiple spectrums of light, it will be possible to map out the few galaxies that lie in this void, and generally confirm its existence in the region they hypothesize. We are constantly moving through space, but even the science of space is always in motion. Each new galaxy, along with data regarding its redshift and travel speed, helps us develop a broader understanding of the movement of the galaxy. It's fascinating to think that not all of that motion is caused by the pull of gravity. It might turn out that sometimes the universe just needs a little push to get going. Can information travel backwards in time? It's the sort of thing that would be really useful if it were true. You could tell your past self not to eat that burrito that didn't agree with you, or you could reveal to yourself the winning lottery numbers. But it just doesn't happen. The resulting paradoxes alone would make the whole thing laughable. In our universe, time always seems to flow in one direction, forward. The idea of traveling backwards in time, or even simply communicating with your past self, seems so outlandish it can't possibly be true. So, why is it that on the quantum level, information seems to be doing just this? What? You haven't noticed particles communicating backwards in time? Well, perhaps we need to talk about the strangeness that is quantum mechanics. It is an effect that, if understood, could one day bring us technologies like faster-than-light communication, or faster-than-light travel. At least, if we could somehow harness it. But even if we can't, it's an undeniably strange insight into the unseen world around us. I'm Alex McColgan, and you're watching Astrum. You're about to see some real-world experiments that are mind-bendingly weird. And if by the end of this video you enjoyed what you learned, feel free to give this video a like and subscribe to the channel. Just please don't break causality when you do. So what do I mean by particles traveling backwards in time? By all accounts, it doesn't seem possible. In previous videos, I mentioned that objects would require infinite energy to even go fast enough to reach the speed of light. So how could something go so fast as to reverse the usual direction of time and arrive at a destination just not instantly, but before they left? Not even light can do that, and it's the fastest thing we know of. Well, this rule about nothing traveling faster than light is mostly true for the macro-scale universe that we live in, and by macro-scale I mean everything significantly larger than an atom. But physicist John Stuart Bell noticed an exception to this rule when it comes to quantum entangled particles. Okay, so let's start there. What is a quantum tangled particle? In quantum physics, it's possible to hit two particles together in such a way as to link them together, so that by measuring the one particle, you learn things about the other. For instance, if you know that the particles originally had a total of 0 momentum, and you learn the momentum of one of the newly quantumly tangled particles, you know the momentum of the other particle will be the exact reverse, making sure the total remains 0. Effectively, by measuring the one particle, you can learn things about the other. This works for other particle properties too, such as position, polarization, or spin. On the surface, there's nothing too weird about this. It's no different from me meeting up with a friend and discussing our plans for the evening. We agree to go out, and we agree that I will pay for the evening and my friend won't. Then, no matter how far we go on our night out, or even if at some point separate, I know I will be paying and my friend will know that he won't. This is how Einstein thought it worked, only it turned out that Einstein was wrong. Because as it happens, me and my friend did not discuss in advance who would be paying. And the strangest of all, we still both agree with each other anyway, 100% of the time, no matter how far apart we are. This is the strange thing about quantum entanglement, and quantum physics in general. We like to think of particles as having fixed properties. However, our first mind-bending experiment shows that particles only have properties when you detect those properties. Until then, they're kind of vague about the whole properties thing, instead only relying on probabilities as defined by a quantum wave equation. This doesn't make sense intuitively. Looking at a thing shouldn't be what gives it properties, right? Well, how would you know? If a tree falls in the woods, does it make a sound? According to quantum physics, not necessarily. Let's talk about the first mind-bending experiment, the Bell experiment. The maths for this is pretty complicated, but bear with me, it's worth the ride. The experiment was first conceptualized by John Stuart Bell, who wanted to know if particles really did have secret properties that they carried around with them, known as hidden variables, or whether they really were making some of it up on the spot. He noticed an interesting mathematical fact about the spin of particles. Before we go any further, I should probably mention that quantum spin isn't the same as normal spin. Misleadingly, quantum spin actually defines whether a particle is influenced, pushed or pulled, by a magnetic field. The name isn't important, but it is important to note that these particles aren't actually spinning and so can have different spin values in almost any given direction. Now, let's take two quantum entangled particles and let's say that we've arranged it so that their spin adds up to a total of 0 between them. This means that if one particle would be pulled by a field, the other will be pushed by it an equal amount along that direction, with the understanding that this doesn't tell you anything about their spin in other directions. One of the features of quantum spin is that if we measure an entangled particle's spin in any given direction, let's say up and down, it will have a 50% chance to be spinning up and an equal 50% chance to be spinning down. But remember, once you measure the other entangled particle, it will have a 100% chance to be spinning in the opposite direction to the first particle. On this fact alone, there is no way to tell if the two particles already knew their spin or are somehow deciding it on the spot and conferring it with each other now that they've been asked. But Bell noticed a clever thing by asking a clever question. If you measured two quantum entangled particles from two randomly selected directions, what are the odds that their spin for different directions would match? Now, let's define that at any time a particle is spinning towards a detector, its spin is up, and any time it is spinning away from a detector, its spin is down. What are the odds that both particles would be spinning up or down when tested? And what are the odds that they would contrast? Let's formalize this with a little experiment. Here we have two entangled particles with 3 detectors reading their spin in different directions. If particle A and B are both red with the top detector, then one of their spins will be up and the other will be down. They are entangled. This is what we looked at previously. However, if particle A is red using the top detector, while particle B is red with one of the other two, these two directions of spin aren't opposites, so particle B has flexibility in which way it goes. Quantum physics claims the particles are making up their attributes on the spot. So once you'd measured the spin of particle A using the top detector, it was a 50-50 whether the spin on the other particle using one of the other detectors would match or contrast. But this is not what classical physics predicted. Let me show you what I mean. Classical physics claims that particles each carry around secret information defining their spin in any given direction. So, for our 3 tested directions, each particle would have a value already. They aren't making it up on the spot. Let's say, hypothetically, our particle's hidden information states up, up, down for particle A and down, down, up for particle B, as B must be opposite to A for each of the directions 1, 2, and 3. Let's pick out a random detector for A. We select detector 1. Detector 1 tells us that A is spinning up. Now let's select a random detector for particle B. We select 1 there too. This detector gives us a reading of down. 1, 1, up, down. We can actually map out all the possible outcomes of this process of random selection in the graph. There are 9 possible outcomes if you were to only measure from 2 detectors at a given time. 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, and so on. For each of these possible selections, we have fixed hidden variable results that we know already, because we hypothetically defined them earlier. Let's fill them in now. Of course, if you detect particles using the same detector on both particles, you'll get a contrasting result because they're entangled. But we're not interested in these results. Classical physics and quantum physics both agree on this, so let's remove them. What are the odds that 2 different detectors for particle A and B will see the same result, and what are the odds they'll differ? Remember, quantum physics expected it to be 50-50. Particles are making up their values on the spot, and so it's perfectly random which they'll choose, as they aren't confined by the opposites rule here. But in this table, classical physics says that contrasting results only happen a third of the time. The other times, they're either both up or both down. If we do this many times, assigning different directions each time, and ignore exceptions, for instance, where the spins of the particles are all up, 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 or down, 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 once you crunch the numbers, the important thing to take from all of this is that according to the maths, classical physics predicts a matching outcome 55% of the time, while quantum physics continues to simply predict 50%. Pretty table be damned. This percentage difference was the key. By quantumly entangling particles and running this test over and over again, you could now see which percentage was correct. And it turned out the winner was quantum physics. Particles were just apparently making up their spin results on the spot, which is spooky. Because not only does that call into question our perceptions of reality itself, but that also means that the moment one particle decided on its spin result, its quantum entangled partner instantly knew that that decision had happened. You could test both particles at once, no matter the distance, and this same result would come back. Somehow, information had traveled from the one particle to the other in no time at all, far faster than light itself. So already something strange was going on here. This result disproved Einstein's predictions and showed that some information does seem to go faster than light. But we can take this one step further and have information going back in time. There is another experiment known as the delayed choice test. Its primary purpose was to explore the fundamental nature of light, whether it was a wave or a particle, and to figure out when it decided to be one or the other. Experiments like the double slit experiment had done this in the past to mixed results. Sometimes light behaved in a wave-like manner, creating interference patterns on detectors that could only happen if a wave was interfering with itself. But sometimes it behaved like a particle, hitting only a single point on a detector. But most baffling of all, it seemed to change which it behaved like depending on whether you were observing its path through space or not. If it could go through multiple paths and no one was watching to see which it did go through, light simply went through both, like a wave. But observed, it went through just the one, like a particle. This result was baffling enough and deserves a video on its own, but in 2006 a number of scientists took it one step further by asking an interesting question. What would happen if you tried to observe the light after it had to pick a path? Consider this experiment. A single photon is sent into a beam splitter, with a 50-50 chance of either being allowed to carry on its way along path 1 or getting reflected up along path 2. Once on either path, the photon is bounced off mirrors, with both paths reconverging here, where the other beam splitter is inserted. Once again, the photon has a 50-50 chance to go either way, with an even chance of arriving at one of the two detectors. If light were just a particle, sending a single photon into this experiment would give you an even chance of it arriving at one detector or the other. You'd not be able to tell which way it went, as the two beam splitters make that impossible to know, but you could see where it ended up. However, this does not occur. When the second beam splitter is present, the light produces an interference pattern, indicating that the single photon went down both paths, ultimately bumping into itself before moving on to both detectors. This seems like strong evidence that light is a wave. It certainly behaves like one here. But what happens if you remove the second beam splitter? Suddenly, you know which path the light traveled down. If light arrives at the top detector, it must have arrived from path 1. If it arrives at the side detector, it must have come along path 2. And something about this knowledge spooks the light. It stops going down both paths, and suddenly, each photon only arrives at one detector. Here's the question. What happens if you insert the beam splitter after the photon has already started down either one or both routes? This is why the test is called delayed choice. If you delay choosing how exactly you intend to detect the photon, whether by knowing which path it came down, or making that ambiguous to you, what happens to the light? What happens is a very strange thing. When this experiment was performed, it was done multiple times, with the beam splitter randomly being inserted or not, but always being inserted after the photon had entered one or both paths. And yet, the results came back unequivocal. If the beam splitter was present, the photon suddenly and seemingly retroactively stopped picking a path. If the beam splitter was removed, the photon seemingly knew it would later be detected and picked a specific path to accommodate. Somehow, the beam splitter being added or removed in the future changed what the photon did in the past. So, what is happening here? Is it really true that particles somehow saw the future? Did the experiment cause information to be sent back into the past? Or is there some other principle at play here that explains this whole thing, that accounts for the instant transmission of information between quantum particles, and allows it to be perfectly rational that light could travel down one path or both at the same time? Personally, I'm inclined to think that this is more likely. We clearly don't understand what is happening here, but it must be admitted, if we don't understand what is happening, there's nothing to say that causality isn't being ignored. In some way, maybe on the quantum level, time really is more fluid than it is up here in the larger universe. Maybe space and time simply do not apply down there. And maybe one day, someone will be able to come up with a theory that allows all these strange phenomena to finally make some sense. Until then, we'll just have to keep asking the same question. Can information travel backwards in time? Until then, we'll just have to all agree on one thing. Quantum physics is strange.
A massive thank you to our astronauts on Patreon. This video had no sponsors, but it was still made possible thanks to the hundreds of members we have there. Link is in the description to join our growing community. Patreon is where Astrum truly takes shape. A place for people who love space, who want to see these videos keep improving and reaching more curious minds. Every new member keeps the channel focused on what really matters, making the complexity of space available to everyone.
If you enjoy what we do, come join the Astrum community today.